Great, thank you very much. It's amazing to see that people still awake and they stay so late to hear about mathematics. So I will talk about some work I did with my frequent collaborators, Jacob Fox from Stanford and David Conlon from Oxford. And it would be about Ramsey theory. So I will explain all these things in the title. So let me just briefly first talk about Ramsey theory. So Ramsey theory refers to a large body of deep results in mathematics which have this underlying phenomena. Every large system has a well-organized subsystem, or in words of Zamotsky, complete disorder is impossible. And currently, you know, over last 80 years, people realize that the examples and applications of this phenomena you can find in many, many mathematical areas like combinatorics and graph theory. Obviously, that was the origin. Logic, that was another origin. But then functional analysis, number theory, computer science, geometry, and information theory. So let me remind you a basic notion in the Ramsey theory. So a Ramsey number, Rkn, it's a minimal n such that no matter how you color k element subsets from the universe of size n using two colors, you will always find a monochromatic set of size n, right? So you probably, you know, all know the very basic fact, right, that the Ramsey number of triangle is 6, right? So, you know, you see this as an example in high school that among any 6 people in this room, we can find 3 which know each other, or 3 which met first time at this lecture. So for this case, my k is 2, right? It's a 2 uniform hypergraph, and my n is 3. So a classical theorem of Ramsey says that these numbers are finite. So no matter which n you take, I can find sufficiently large universe such that, for example, if I color all the triples of this universe red and blue, I will find a subset of size n such that all triples over this subset are red or blue, right? So they have the same color. And one of the main questions which people study in the last 80 years was how fast these numbers are grow. And despite that we try very hard to understand how fast these numbers are grow, we're still very far from understanding it, right? So we know, for example, even in the case of, you know, k equals 2, right? I didn't write here, maybe I should have write here 2, right, pairs. We know that R2, 3 equals 6. We know that R2, 4 equals 17. If you ask me what is R2, 5, we already don't know, right? So such a simple question, right? So how big should be a universe such that if you color the edges over this universe using 2 colors, you find a monochromatic set of size 5? We don't know. Moreover, we even don't know how fast these numbers are grow, right? We have an estimate. We know that these numbers grow pretty fast. So again, if I'm talking only about edges, right? You take a complete graph and you color its edges red and blue, and you're trying to get a monochromatic set of size n, then your complete graph should be of exponential size. But if you ask me what is the exponent it should be, we already don't know this. We know that if your graph is of size 2 to the 2n, then you always find a monochromatic set of size n. And there is a construction of R' using a famous probabilistic method where it shows that 2 to the n over 2 is not enough. So you can find a coloring of the complete graph on 2 to the n over 2 vertices with no monochromatic set of size n, okay? But here we at least understand that this thing grows exponentially. Now, the minute we move to a 3 uniform hypergraph, so again, let me remind you, now we have a big universe. Now I color not the edges, not the pairs, but I color the triples using red and blue. And again, you want a monochromatic set of size n, where all the triples have the same color. How big should be my universe? So here we know even less, right? So we know that if your universe is of double exponential size of 2 to the constant times n, then I can always find a monochromatic set of size n. And on the other hand, we have an example, which is again in probabilistic construction, which shows that 2 to the constant n square is not enough, right? There is a coloring of this universe of triples using red and blue with no monochromatic set of size n. Okay? So why I'm telling you about this thing? Because it would be a little bit related to what I'm going to tell later. So let me make some remarks here. So if we go for larger values of k, right? So instead of coloring triples, we color 4 tuples, 5 tuples, and so on. There is a similar gap between upper and lower bound, which we have of 1 exponential, right? So here you see this is more or less exponential function in n squared. This is double exponential. So if you go to the R4, to the 4 uniform case, this would be triple exponential. This would be double exponential. And actually, the case k equals 3 is very crucial. So the minute we understand this case, if we could have decided, is this an answer or this an answer, we could have understand the Ramsey number for all uniformities. And the reason for this is this ingenious construction of Erdős and Heinel. So what Erdős and Heinel realized that starting from k equals 3, you can amplify the construction. So if you give me a construction of coloring of triples of some universe without monochromatic set of size n, I can construct you a coloring of 4 tuples of the universe which is exponentially bigger than the universe for triples, which also doesn't have a monochromatic set of size maybe 2n. So basically, once you understand the triples, you can plug it into this machinery called stepping up lemma and produce a similar construction for high uniformities, gaining an exponential function every step, right? So once, if I, for example, can show you the construction of R3n, which is also doubly exponential, then for 4 uniform set, I will get construction which is triple exponential and so on. Okay. So this would be related a little bit to the problem I actually want to talk about, mostly, where somehow it looked like in the beginning we had completely the same problem. We had the same difficulty, but somehow we managed to overcome this difficulty. And the proof which I'm going to show you would be very much similar what people were trying to do for hypergraphs, but actually in that case we succeeded doing it. So what is the problem? So it would be a Ramsey type questions for words and patterns. Okay? So please now ask me questions if some notions are not understood, because they will play a crucial role for the rest of the talk. So I have some alphabet, and my words would be, you know, just a collection of letters from this alphabet, and the order matters. And pattern would be a string of characters, maybe over some other alphabet. Okay? So now what is a subword of the word? Subword of the word, you just take a block of consecutive letters, right? So if you take word mathematics, M-A-T, it's a subword, right? It just appears consecutively in the word of mathematics. Now, the next notion I need, and this is a main notion, I say word W contain a pattern P if there is a way to substitute, instead of every symbol in the pattern T, a non-empty word over my alphabet, but the most important thing, over the same symbols I have substituted the same word, such that the resulting object which I get would be subword of W. Okay, so let me give you the example and spend some time on it so that we understand it. So again, let's take a word mathematics, and then I claim that this word contains a pattern of the form X, Y, X, Z. So to show you this, I need to take this English alphabet, substitute something instead of X, something instead of Y, but then again the same thing instead of the second X, right, because this should be the same, and then something instead of Z. And so I claim that if I take X to be M-A-T, Y to be H-E, and Z to be I-C-S, then I get indeed that mathematics contain a pattern X, Y, X, Z. Is it clear? So again, so you give me a favorite pattern like X, Y, X, Z, then you give me very long Russian word, and then I need to substitute something for X, some collection of Russian letters, then something for Y, then if X appears again, whatever you decided first time, you cannot change it. You should put exactly the same, right? You see that this M-A-T I put here and I put here, right? Math, M-A-T and my M-A-T, and so on. And I'm getting a sum word, and I want this word to be a subword of my W, right? So I tell you that the pattern appear in my word if I can assign to every symbol some collection of letters, and then what I get would appear consecutively. It's very important. It will appear consecutively there. Okay. So what I would be interested in the following kind of Ramsey type question. You take a very, very long word, and then you ask what kind of pattern you can find there and what kind of patterns you cannot find there. Okay? So let me give you a definition. So the pattern P would be Q unavoidable if every sufficiently long word of an alphabet which has Q letters, right, contains a copy of P. Right? So I say mathematics is unavoidable if I take sufficiently long, I don't know, word of English alphabet. It would be 26 unavoidable because English alphabet, if I remember correctly, has 26 letters. So if I take sufficiently long word of an English alphabet, I find the pattern, I don't know, X, Y. So I say the pattern X, Y, X, Z is unavoidable if I can kind of substitute something there, like mathematics, and find it. So the study of which patterns are avoidable and which patterns are unavoidable has a very long history. It goes back more than 100 years to Tuohy, where Tuohy realized that the pattern XX is 2 unavoidable, but it's 3 avoidable. So what does it mean the pattern XX is 2 unavoidable? It means that if I take a long binary words, right? My alphabet has 2 letters, let's say 0 and 1. I would not be able to avoid pattern XX. So what does it mean? I would not be able to avoid something and exactly the same repetition of this something immediately after it. And this is very easy to see, right? So you start your pattern, and you start it, let's say it doesn't matter. You start it either with 0 or 1. So here is 0. Now if I write again after the 0, 0 again, I got my XX, right? So I cannot, right? Because I have a repetition. So I need to put here 1. And now after this 1, I cannot write 1 again because I again will have XX. I will have to write 0. And again after the 0, I cannot write 0 because I again get XX. I write 1. But now I'm dead, right? Because I got this XX. Okay? So pattern XX is very easy to see is unavoidable of alphabet of 2 letters. Actually, any word of length 4 already contain it. And it's quite remarkable that Tuohy constructed an infinite word. So as many letters if you want of an alphabet of 0, 1, and 2, which in no place contains an X. So you would not be able to identify a word, some pattern X, like the same collection of symbols, and then immediately the same collection. The collection of symbols and the same collection of symbols immediately after it, right? So when I say 3 avoidable, I mean that there is an infinite word where pattern of alphabet of size 0, 1, 2, where pattern in X does not appear. So another result, roughly in the same time, was also obtained by Tuohy, and was obtained by Marston Morse, who actually was a topologist in Institute for Advanced Study. And Morse was interested in certain questions about dynamical system, and they naturally lead him to this pattern avoidance thing. And what they observe is that pattern XXX, so I want a triple repetition of something, right, of the same thing. Obviously, in 1 unavoidable, if you have alphabet with 1 letter, let's say 0, that the 3 times you use 0, you already got XXX. But remarkably, you can have an infinite word using 0 and 1, where pattern XXX does not appear. And actually, this time I can tell you how the construction works. And many times that's how people got in this area construction. The constructions are recursive. So you take, let's say your alphabet has letters A and B. So you start with, let's say, with the letter A, and then in the next time you substitute instead of letter A, B, and then you look on the symbols, and again, instead of A, you substitute A, B, and instead of B, you substitute B, A, and then you continue. And what you can prove that if you continue building your word, what obviously doubles every time, and no matter how long it will get, you will never get XXX, okay? So that's early results in this area. Actually, by now, the examples of pattern avoidance appear in many areas of mathematics. Obviously, this is a very natural combinatorial question, but there is this whole area of group theory about undecidability, right? So there the question is, I give you a group with some set of generators, and then I tell you that certain words in these generators are identities, and I give you some other very long word, and I try to decide whether this word is an identity. So apparently this problem is undecidable. So it means there is no algorithm which will run finite time and will tell you the answer. And to prove undecidability, somehow it naturally leads to this type of problems. And as I already mentioned, symbolic dynamic and number theory and so on. Okay, so that type of questions I want to study, and I want to study them from the point of view of combinatorics. So the next definition is crucial. So I say that pattern is unavoidable if it's unavoidable no matter how large alphabet you take, as long as it's constant, right? So we saw that there can be patterns which are 2 unavoidable by 3 avoidable. There were patterns which are 1 unavoidable but 2 avoidable. So I want to know, are there patterns which are unavoidable? So it means that no matter how long alphabet, how big alphabet I take, but fixed size, if I take sufficiently long word in this alphabet, I will see this pattern, right? So this is a Ramsey type questions, right? Because we said, right, Ramsey theory looks for certain ordered systems in large, certain ordered subsystems in the large system. So which patterns are unavoidable? So surprisingly, you can give a very nice characterization for this type of pattern. And it was done by Zimin in 1984 and simultaneously by Bean, Ehrenfeucht, and McNulty. And basically, they tell you, actually, the characterization is from the paper of Zimin. This guy said it a little bit more complicated form, but it tells you what kind of patterns are unavoidable. So you can define these patterns recursively. So the pattern, let's call it Z1, is just one letter. Obviously, one letter pattern is always unavoidable as long as your word has non-zero length. But the next guy, so if you know that one letter pattern is Z1, so what is Z2? Z2 will look like X, Y, X, right? So let's write it. So this is Z1. So you define it recursively. So Z2, you take 2 copies of Z1 with the same X, and you stick in between them new letter. So Z2 is X, Y, X. So apparently, no matter over which alphabet you take sufficiently large word, I will always find you something which I can call this X, and they separate it by something, right? Y can be anything. And then this 3 is again, you take 2 copies of Z2, so you take this X, Y, X, X, Y, Z, and you take a new letter between them. And similarly Z4, and then you got the idea, right? So basically Zn is, you take 2 copies of Zn minus 1, they have to have the same symbols, and you stick between them a new symbol. And no matter how long you will have a word of a fixed alphabet, you would not be able to avoid any of these Zi's, and obviously any subword of them, right? So when I say that these characterize your all patterns, it means these are the biggest patterns which you cannot avoid, and obviously any subword of them you cannot avoid as well. Any questions? So maybe let's write it. So did I put them? So again, so Z1 is X, Z2 is, you take 2 copies of Z1 and stick a new letter between them. So Z3, again, you take 2 copies of Z2 and you stick a new letter between them, and so on, right? Right, so let me say a few words about that. So just let me write Zn. So Zn, it's, you take 2 copies of Zn minus 1, and then you take a new letter, right, between them. Okay. Great, so what is a natural question you can ask? So now we know that they're unavoidable. So it means if I write you long enough word of a Russian alphabet, I will always find something which looks like Z3. So I can put some Russian word instead of X, some Russian word instead of Y, some Russian word, the same word instead of X, some new word instead of Z, again the same word instead of X, again the same word which I already used for Y and X, and I will find this consecutively in this long word you wrote. So if you come from Ramsey theory, what is the natural question you ask? So you know that you cannot avoid this pattern. So how long should be a word after which you see the pattern you wanted, right? So I told you there is no infinite word. So the natural question is, can you estimate me how long I can go until I must find, for example, pattern which looks like this three, right? So you give me your alphabet, let's say, I don't know, over some, so let's say English alphabet, 26 letters. So my Q is 26. So how long I can write word using English letters without having this pattern? So this is a question I want to ask, right? So, So F and Q, it's the longest word I can write over alphabet with Q letters, which would not contain or more correctly, so if I have the word of this length, I will have to contain the n, right? So it's the longest word which guarantee me to find a copy of the n. Is it clear? So I know that it's finite. Now the question is how big this guy should be. And so, as I said, so the natural question, I want to estimate the asymptotics. And sorry? Y can be the same as x, right? So when I tell you that this, so you need to substitute something instead of y, by no means I mean that it should be different on x, right? The only thing which is the rule requires, if I have x here and I have x here, I have to be is the same word. If I put here mama, then mama should appear here as well, okay? So it's very easy. The same thing should be the same. The different thing can be similar to the x as well, okay? So let's see the bounds. So in the beginning, it all looks very easy. Obviously, so if you want to find z1, it's just one symbol. The minute your word has length 1, you found x. Now let's think about z2. So z2 is this. So now observe that if you have some letter of your alphabet appear 3 times, then the first appearance and the third appearance of this letter will have something in between which you can call y, and therefore you will find z2. So if your alphabet is of length of size q, the minute you have 2q plus 1 symbols, some symbol will appear 3 times and you're dead. So obviously 2q plus 1 is upper bound. And on the other hand, if I'm trying to avoid z2, I can do it in the length of q. So I can first take 2 zeros, and then 2 ones, and then 2 twos, and then so on, and then qq, right? And this is the length of 2q, and it would not contain, so this is what I'm trying to say, it would not contain z2 because every appearance of the same letter would not be separated. So is it clear? So a little bit more work will require this bound, that if you try to find me z3, then the upper bound which you can get is of order q to the q. So it's now jumps, right? It's 1, q, and now it's exponential. It's q to the q, okay? So let me at least give you the idea why this is the case. And to give you the idea, so what I want to prove, and I'll write you precise lemma, but I roughly want to prove that f and q behaves like q to the power f n minus 1q. So basically, if you're trying to avoid Zn, it's more or less exponential compared to how much it took you to avoid Zn minus 1. Right? And therefore, it would be very much reminiscent of Ramsey numbers for hypergraphs, right? When you, so whatever would correspond to uniformity of hypergraph would be this n. Every time you go to the next uniformity, we think that everything exponentiates. But this upper bound would be very simple. So I'm trying to show you that the longest word without Zn plus 1 is at most, this is the main term, roughly q to the power, the length of the longest word avoiding Zn, plus some another multiplicative factor of f and q, but obviously this exponential is way bigger than this. Now this is a very simple pigeonhole argument. So you give me a very long word. So give me a word of z length of the alphabet of q letters. So what you do, you take this word and you split it. You take W1 to be the first F and Q letters of your word. Then you take arbitrary symbol, which is there. Then you take W2, which is again that many letters of your word. Then you stick another symbol. Then you again take F and Q letters of your word and so on, right? So basically, if you have a word of length like that, then you can split it, right? So you can do, so you take F and Q guys here, then something, then again F and Q letters here, then again something, and so on. And if you word long enough, then you get really many of these guys, right? So you get many of these intervals. How many? Q to the F and Q. Now, why this is good? Because, you know, if you have more than Q to the F and Q such intervals, two of them would be the same, right? Just because your alphabet is of size Q and the length of the word is F and Q. So if there are many such subwords disjoint in your word, then two of them are the same. Now, because of the definition, right, this W1 should contain a copy of Zn, right? Because W1 was long enough to contain a copy of Zn. And W2 was long enough to contain a copy of Zn, and so on. But if you have, let's say, W1 and Wm are the same, then obviously they contain the same copy of Zn, and they separate it. So then you get a copy of Zn plus 1, right? So you basically take long enough words such that if you split it into pieces of length F and Q, two pieces would be the same. They would contain the same copy of Zn. They would be separated, so therefore they would contain Zn plus 1, and you'll see that this just exponentiates, okay? And so therefore you will get this theorem, right? We already know that F3Q, maybe let me move it a little bit here. We already know that F3Q was Q to the Q. So then you plug it into this formula, and you get F4Q would be Q to the Q to the Q, and so on, right? So you get this tower type function, right? And again, it's very much similar to what we know about hypergraph Ramsey numbers, right? So the Ramsey numbers for graphs is exponential, for 3 uniform hypergraphs is double exponential, and so on. So this is an upper bound, which comes very cheaply, just pigeonhole argument. So the question which is natural to ask, how good is this bound? And the only result which was in this direction was by Cooper and Rohrabaugh, who studied this problem. And what they showed that F and Q should grow at least as Q to the 2 to the n minus 1. Now, what I want to make a remark here, don't be misled by the structure of this function. Remember that your n is constant, right? So your n is 3. So if your n is 3, it's just Q to the 4, right? So it's actually only polynomial lower bound, right? So that's what I'm writing. So for any fixed n, this bound is constant degree polynomial in Q, whereas the upper bound which you have is tower type, right? So the gap is huge. Right? So the natural equation, which when we saw it, we were quite surprised that there is such a gap. And so the natural equation, how fast should this function grow? So again, I want to know how long is a word should be over alphabet of size Q, such that it will contain Zn, nth Zeeman word. And so what we managed to do, we managed to resolve this question. So that's what I said. It would be very similar to hypergraph Ramsey numbers, but this problem is way more easy. But the structure of the proof would be the same. So we managed to show, and actually this is quite surprising. There are not so many Ramsey type problems which we know which grow as a tower type, which we know so accurately, right? So note that not only I know that it's a tower of the right height, I know that the last exponent is a correct one, right? So if I take n minus 1 times log and divide it by q, both upper and lower bound constant would be tending to 1, right? So I really know this function quite accurately, right? So for large alphabets, we really know how long the word should be. It should be q to the q to the q n minus 1 times. Now, another remark which I will not talk about this only works for large alphabet. And I'll give you a sketch of the proof, and you'll see that I need in this proof that Q is very, very large. But we actually can deal with alphabets which are small as well. So even for binary alphabet, right, if you're trying to avoid Zeeman word of length n, we know that the growth is still tower type. And finally, what I want to mention is we have a very nice construction in both the proofs where we know F3Q really accurately. So again, this is quite unheard of in terms of Ramsey numbers for graphs, right? We not only know that it's of order Q to the Q, we actually have quite accurate formula. So it should be, so if I want to guarantee you the existence of Zeeman word, right, Z3 of alphabet of size Q, then my function should be of order 2 to the Q times Q factorial, and the only thing which I don't know is the constant between, in front of the thing, and the gap between this upper and lower bound is less than 7. So we roughly understand what's going on there. Okay. So any questions? So again, so is it clear what the result and what the problems? So again, I want to I have an alphabet of size Q. I want to take a sufficiently long word over this alphabet, and I want to know how long is this alphabet this word need to be. So for example, in order to see pattern like that, and again, pattern like that means I can substitute some word instead of X, instead of Y, and instead of Z, and more importantly, that this copy of X and this copy of X should get the same word, and then I want to see this consecutively. And the main goal would be to try to get a lower bound. Okay, so try to construct a really, really long words which will avoid this type of things. So any questions? No, it's n minus 1, right? Right, it's exactly, so that's why I said, right, we really know the tower, and we really know even that the last term should be, the upper bound has here Q, and the lower bound will have Q. For N2, right, but note that this height is like a constant, right? The difference, if your Q is 2, the difference between n minus 4 and n is just 16, right? So it's, I could have write 16. Right, so not 16, but it's 2 to the 2 to the 2 4 times. It's a constant number. Any questions? Okay, so as I said, I would be interested to prove use this. Right? And the proof would be very similar to what people try for hypergraph Ramsey numbers, just for us it will work in this particular case. So the proof will have 2 steps. So first, we will try to deal with the case of words avoiding these 3. So I will try to show you that there are words of length, right? So I will try to show you a construction proving that F3 to the Q equals Q to the Q minus little of Q, right? So I will try to show you this. But actually, and then, right, so maybe let's write the second step, and then I will try to have a stepping up procedure which will do amplification. So once I will have this, I will try to show you that I can use this construction to construct something which shows that F for Q is Q to the Q to the Q, right? So if I have a long word avoiding Z3, I want a long word avoiding Z4, and I want to use this long word avoiding Z3 there. Now, unfortunately, we realize that we need a little bit more. So not only I need to show you that there is a word of length Q to the Q which avoids Z3, I need to show you that there are really a lot of words like that. So if you think you have alphabet of size Q, if you're looking on the words of length Q to the Q roughly, how many such words are there? It's Q to the Q to the Q. It's like triple exponential. So what it appears we need in our proof, and we can get it, is that, not only that there exists a long word of order Q to the Q avoiding this 3, but we really need a count. We need to say that most of the words of length Q to the Q will avoid this 3, right? And once I have such a statement, I can do amplification. So is it clear? So it's actually quite surprising. It's a stronger statement. So we show that there are really not just a particular strange word of length q to the q which will not have pattern. There are really as many as it can be. Of course, I'm cheating here, but of order q to the q minus little of q words of length q to the q which avoids these three. Okay? And then I do amplification. Now let me tell a few words about how we're going to prove it. Right? And then I'll show you the second part. So because I'm telling you that almost all words of length q to the q, I want them to avoid these three, the way to show it, it's kind of natural to use a random word. Okay? So the idea would be use random words. The problem is that if you do it naively, it somehow doesn't work, because in truly random word, so if you take 3 consecutive letters, the probability to see here x, y, x, so the probability of this is order 1 over q cubed. Right? Because every letter is at random, you have q letters. If you put your letters at random, fix arbitrary 3 positions, the probability to see whatever you want there is 1 over q cubed. So therefore, if you take your random word of length bigger than q cubed, just this particular thing will appear again with overwhelming probability. Right? It's a large deviation inequality. So you would not be able not only to get an exponential, you would not be able to beat a q cube, right? So in order to overcome this, you somehow want to make it very difficult, right? What was our problem here? So our problem was here that this is a copy of Z2, and the copy of Z2 is very short, and it would appear there if I'm very not careful. So what instead we want to do is we want somehow to make it very difficult for Z to appear. And if every copy of Z2 is really, the x's are very far apart, then in between there should be many, many letters. So therefore a repetition of such word would be highly unlikely. And there is a very cheap way to achieve this. So it's the following. So you take your alphabet Q, and you, let's say you take your T being of log Q, some function which is growing much, much slower than Q. Let's say log Q will do. And you split your Q into T subsets, right? So you split it into 2 T subsets. L1, union L2, union LT, right? Every Li is of order, let's call it S, roughly of order Q over log Q, right? So I take my alphabet, and I split it into some number of parts, such that the number of parts tends to infinity. And now how I will construct my random word. So I will take here the first interval, I1, and it would be a permutation of L1. So I take L1 in random order. Right? Just take this bunch of guys here at random order. And then you take I2, and it would be permutation of L2, and so on. IT would be permutation of LT, and then and then you continue. Now it's no problem. Now you again, right? IT plus 1 would be again permutation of L1. So basically, you take this interval and you put them into random order, and when you already, after T steps, you just reuse it. IT plus 1 would be permutation of L1, and in generally, right, if you have an interval J times T plus L, then this would be a permutation of L. Right? So basically, you go and just repeat this interval, and every time you take a random permutation. Why this resolves the issue which I had before? Because now in order to repeat the letter, right, the letter which you saw in I1 would not appear here because this was a disjoint set of letters and will not appear here and will not appear here. You basically only can see again this letter here, very far distance away, right? So the observe between repeated letters distance is s minus 1 times t, which is very close to q. So basically, by doing this, I'm creating you a random word where two letters can repeat itself only after you see q other letters, right? So if this is the case, that it means that the shortest copy of Z2 which you ever will have has length q. And now in order to get Z3, you need to have a 2 copy of Z2 repeated. So if you know this guy has length q and this guy has length q, and you're putting, you know, permutation doesn't do much in terms of your counting. I might as well would have sampled letters at random, but I cannot guarantee you that the same letters would be far apart. But if I do it like that, then the probability that this word repeats itself is roughly q to the q. So let's do the computation, right? So note that probability to repeat a word of length equal s minus 1 times t, which is roughly q, is the following. Sorry, it's s times t minus 1. T minus 1 times s, right? Because, again, every guy is of size s, and I can repeat only after I already see t minus 1 intervals. So the probability of this is s factorial, right? I need to see the same permutation of every single guy. And now note that your s was q over t, and then you're putting it to the power t minus 1, it's roughly of order q to the q, right? So basically, you know, this is the only thing which you need to observe, that by doing this permutation, probability to see a word of length q repeated is more or less like it would have been random procedure, right? It's q to the q. And therefore, now you can believe me that if I take a word shorter than q to the q, I just don't see 2 repeated words of length q. And because every copy of my Z2 should be of length q, I will not see Z3. Moreover, you can use this tool which was mentioned by Peter called local lemma to show that not only I will find a one word of length q to the q which have this property, but I have plenty of words. I have roughly most, I mean, in asymptotic sets, I will have q to the q words of length q to the q which avoids this three. So that was first ingredient, to realize that you can just randomize, right? What you want to do, you can randomize the construction, but you cannot do naively just pick a letter at random, simply because the copy of Z2 appears too often and too close to each other, right? So the minute you can guarantee me that the repeated letters would be far apart, there is a random way of doing this such that every copy of Z2 would be very long, and therefore every copy of Z3 would be even longer, and so on. Okay, so this was the first observation. Now, in order to amplify what I want to amplify, I need a little bit more, I need a slightly I need one additional trick, right? So far I I explained you how to construct a very long word, which does not contain a copy of Z3. So what I really want, I want to construct a really long word which not only does not contain a copy of Z3, but I actually, know where the copies of Z2, how they look like. So basically, let me give you a definition. So let me denote by S and Q a collection of words over alphabet of size Q with distinguished letter. It would be important for me to amplify with distinguished letter, let's say D, such that any subword not containing D avoids Zn minus 1, avoids Zn minus 1. So what I actually can do, what I want to tell you, that in this random construction, right, where I take the first interval at random and second and so on, I can stick here a new letter such that not only that I would know that in this word there are no Z3, but I would know that every Z2 which have to contain this letter somewhere, right? So I somehow can pinpoint these copies of Z2, and it's very easy to do, right? So if you remember, I took the first interval permutation, second, and so on, and then I came to the interval IT, and then I started IT plus 1, which was a permutation of I1. So if I stick here the letter D, then you know that any copy of Z2 which have contained it, because any copy of Z2 should have a repeated letter, and the only repetition of the letters here happens here. So you should have D in between, right? Because you have X, and then everything in between you have to take it, right? So basically what I can do, I can show you, right, that the longest or the number of words in S3Q is roughly Q to the minus little of Q. So not only I can take this construction, but I can make these words in such a way, I can add a new letter and we'll stick it here between, like I once see all the letters, and I stick these and all the letters and so on, and I would know that every copy of Z2 which have contains this D. Is it clear? So again, so my construction allows me to add a distinguished letter to the picture, such that not only in this long word there would be no Z3, but I will know how Z2 looks like. Z2 will have contained this copy of this distinguished letter. Now, once I have it, we have the following stepping up procedure. So the stepping up procedure says the following. Imagine you look on all words of an alphabet with Q letters, where one letter D is distinguished letter, and you look on all words which are avoiding Zn, and moreover, they are such that the subwords of your words which does not contain this distinguished letter D, they avoid Zn minus 1. So it's precisely this situation, right? So I have long words, they avoid these three. Moreover, if I take a subword of this word which does not contain this distinguished letter D, it avoids Z2. So then what I can do, I can go and increase the size of the alphabet only by 2 and exponentiate the number of the words, right? So look what this inequality says. So now if you tell me how many words of length n of an alphabet of size Q which have this property, right? It avoids the n and it has distinguished letter D, which if you don't contain it, you don't have Zn minus 1. Then I can take an alphabet at 2 letters, which basically Q or Q plus 2 doesn't affect your asymptotics, and create you many, many more, right? A factorial number of the previous guys, the words which now avoid Zn plus 1 has distinguished letter, such that if you don't contain this letter, then you avoid Zn. And now I can amplify, right? And note that this would do this precisely what I want, right? It goes from the number t to t factorial. And from t factorial, right, t factorial factorial. But if you think from t to t factorial is roughly like t to the t, and so on. You amplify it. So this will give you exponential growth. And the construction is really simple. So I tell you the construction, and then we'll just, you know, you need to check that whatever I'm telling you, I'm not cheating you. So again, so you write all the words which you have, right, which like W1, WM, things that these are all the words of alphabet with Q letters. Each W has a distinguished letter D. Each W doesn't contain the N. And moreover, if you don't contain this distinguished letter, you don't contain the N minus 1. And I want to show you that there are many letters, many more words I can construct which have this property, which do not contain the N plus 1 of alphabet of Q plus 2 letters. And again, having distinguished letter, which if you don't contain it, you don't contain the N. So I take any permutation of these guys. Just note that if I have m of them, that the number of permutation would be m factorial, right? So this is precisely what I want. Now I just massage them to have my property. So what I do? So suppose the C was distinguished letter in every single of these words, such that if I don't contain C, I already don't have ZM minus 1. So I take, and in W1, instead of C, I put C0. And in or maybe in W1, if I don't have C, I put C1. And in W2, if I don't have, if instead of C, I put C0. So basically, I go over all my words, and if this word appears in the even position, I substitute this distinguished letter C by C1, and if it appears in even position, I substitute by C0. And that's it. And now I claim that, you know, so right? And moreover, I stick between them, between W and WN, a new letter D. So basically, that would how my word looks like. So every U1 would be a copy of W1 such that the letter C was substituted by C1. U2 would be a copy of W2 such that the letter C would be substituted by C0. U3 would be a copy of W3 such that, again, the letter C would be substituted by C1 and so on. And moreover, between them, I stick the letter D. So now let's do the at least math in terms of the size of the alphabet. I started with alphabet with Q letters. So there was this distinguished letter C. I throw it away, I lose 1. And then I add 2 letters, C0 and C1. So far I increase the size of the alphabet by 1. And now I add this new letter D, so I increase the size of the alphabet by 2. Now what I claim is that no matter in which order you write these W's, after you did this new substitution, you get a new word which avoids the n plus 1, and moreover, any copy of the n should contain a distinguished letter D. Okay? And this, because I can do it for any order of W, from some bunch of words, I get the number of new words, which is a factorial of the previous guys. So that's basically the idea, right? So you first show me that you know to solve the case of these 3, and then you show me how to amplify it, and that's how we amplify it. Okay? And I will not go too much in the detail, not to bore you with them. So I want to finish with one problem, which I think is really, really nice, and which we have no clue how to solve. So what is the problem? So I already mentioned to you that this pattern x, x, x is 2 avoidable, but not 1 avoidable, right? That was a Morse 2 sequence. Then I mentioned that the square x, x cannot be avoided of alphabet with 2 letters, but can be avoided with alphabet with 3 letters. Okay. So then what would be the natural thing to ask? Okay, is there something which cannot be avoided of alphabet with 3 letters, but can be avoided with alphabet of 4 letters? And the answer is yes. But now it looks already not so nice, right? So you can imagine somebody spent some time with a computer to find this pattern, right? So this crazy pattern cannot be avoided of an alphabet with 3 letters, but there is an infinite word of a 4-letter alphabet which does not have this pattern. Okay, so let's go further. So what about 5? So now it's even more crazier pattern, right? It's a paper which has a lot of computer assisted proof, which cannot be avoided of alphabet with 4 letters, but can be avoided. There's an infinite word of alphabet with 5 letters. And here we stop, right? So the natural question, and I'm sure that the answer is yes, that for every Q, there should be a pattern which cannot be avoided of alphabet with Q letters, but there should be an infinite word of alphabet of size Q plus 1, where this pattern already does not appear. And this is an open question. We don't know it beyond 4 and 5. And let me stop here.